So this is a project on a full bridge load cell analysis for mechanical engineering class ME 3870. This team was made up of Jose Lozada, Thomas Francine, and Jianqi Guo. So the project objective was to investigate the full bridge load cell measuring system by performing a control experiment to analyze the static and dynamic response of the system. The physics operation for this system was a load cell that worked on the principle of a strain gauge. That is, the gauge induces a resistance within a circuit. As the gauge deforms with axial strain, the gauge length alters respectively, thus adjusting the electrical resistivity of the gauge and producing a relative change in voltage output. For the experimental setup supplies, this system utilizes a load cell, a tuning potentiometer, an instrumentation amplifier, assorted resistors, jump wires, and a MIDAC system. Since the MIDAC is not able to generate much current, an external power supply was used. A power supply of 15 volts was used. A voltage divider and a potentiometer were used to achieve the voltage required to power the load cell, and this required voltage was 10 volts. Once the setup was completed, the team moved forward to perform the static calibration of the full bridge load cell. This was done by clamping the load cell onto a table and making sure the load cell was oriented correctly. After this, the team recorded voltage and load data for an increasing and decreasing amount of load. This process was carried out for 8 iterations. After collecting the data from LabVIEW, the data was then extracted to MATLAB. After plotting voltage versus load and performing an LSRM, the sensitivity of the load cell was found to be 0.426 volts per kilogram. And here are the errors that we calculated throughout our system with an overall uncertainty of plus or minus 0.0135 kilograms. Once the static calibration of the full bridge load cell was completed, the team moved forward to perform the dynamic calibration of the load cell. With the same setup, students struck the load cell with a striking hammer while continuously recording data. This process was repeated 3 times. After exporting the data from LabVIEW and performing a fast Fourier transformation and a logarithmic decrement, the natural frequency of the load cell was found to be 1200 Hz with a damping ratio of 0.0557, meaning the system is an underdamped system. Here are our summary results. Through static analysis, we found out that our static sensitivity is 0.462 volts per kilogram. Through dynamic analysis, we found out it was a second order system with a natural frequency of 1200 Hz and a damping ratio of 0.0557. And since it is under 1, it means it is an underdamped system. Our design state uncertainty was
8.303 times 10 to the negative 4th kilograms.
And our overall uncertainty was plus or minus 0.0135 kilograms.